Proxima b, the enigmatic planet that captured the public's imagination back in late 2016. But how was that planet discovered? Today, we're going to find out the answer to that question.
Science Violation.
Welcome back to our show Science Violation with your host, Professor Jenkins. And today I'm joined by a colleague of mine, Dr. Mikko Tuomi. Mikko, how are you feeling today to be on the show?
I'm feeling alright, thanks for having me here.
My pleasure. And today I've invited Mikko here to talk about a specific topic, and it's a topic that most of the public, when they interact with me, enjoy to question me on, and that's the topic of Proxima b, the discovery of Proxima b in particular. Now there's two themes that the public generally, you out there, enjoy talking about, and that would be one, is there life on this planet? Could there be life on this planet, and what's your thoughts on that? But the other one, and maybe more importantly at this time being, is how did you discover Proxima b? How was that planet made? So Mikko, I want to take you back to the beginning, and I want to know your thoughts. How was Proxima b discovered?
Well, that would be going back to 2012, when I was looking at data taken for a sample of 40 different nearby M dwarfs in a solar neighborhood.
Nearby M dwarfs. So M dwarfs are, what kind of stars are M dwarfs?
They are red dwarf stars, less luminous than the sun, and there's just massive amounts of them. There's about 10 times as many as there are G dwarfs, like our sun, in the universe.
Yeah, around 60 to 70% of all stars are these so-called M stars, these really small, long-lived stars.
Yes, that's correct.
Yeah, and so you were searching a sample of these stars. Why?
I wanted to see what happens if I analyze the data from two different instruments in a simultaneous manner, so that you could possibly see signals of planets not seen in either instrument alone.
Okay, and was that a common technique at the time? How did you make that discovery in the end? Why did you start that investigation?
I wanted to look at statistics of planets orbiting nearby stars, and well, I had to choose one sample of dwarfs I could easily look at with available data and with techniques I could use to analyze it. Okay,
and that sample, what was that sample? What made it important?
It was important because it consisted of very nearby M dwarfs, and there were plenty of data from two different instruments, and because the sample had already been analysed in the literature, so we knew the properties of the stars and we knew reasonably well what to expect.
And that's a key point to the survey, right? That we already knew a lot about this sample of stars. That was a key element of the survey.
Yes, and Proxima Centauri, although it's the nearest star to the Sun, it was only one of these stars in this sample, and we didn't expect much special about it.
Yeah, so Proxima Centauri, as you just mentioned, is the nearest star to the Sun, and it orbits the bright, well-known binary star Alpha Centauri A, Alpha Centauri B, and it orbits those stars in about 500,000 years or so, at least that's what we believe. And so, being the closest system to the Sun, what does that mean? Why is that important?
Of course, we want to know what our solar neighborhood looks like. What are the nearest exoplanets to our own solar system? And that's in a perspective of possibly sending robotic probes and visiting them in the near future.
And that is a key point. Being the nearest to the Sun is going to be the first port of call if we can traverse the great distances between the stars.
That's a big if, I might say.
Yes, because we talk about Proxima b being the closest planet to us, or the Proxima Centauri system, but that's 4.2 light years away. That's 25 trillion miles. 25 million miles. That's not a small distance.
No, of course not.
Okay, so coming back to the sample, what did you discover?
We discovered that there's, on average, more than one planet orbiting each M dwarf. That was back then. Now we know there are more than 3. But regarding Proxima Centauri, we discovered at least 4 distinct periodic signals in the radial velocity data. And out of these, one of course is our familiar Proxima b, but there were others, and we were not at the time quite sure what was the cause of these signals.
So there's two key points here, and I want to come back to both of them. One, each M dwarf in the galaxy, certainly in the solar neighbourhood nearby our Sun, has at least 3 small planets, or 3 planets in general, in orbit.
That's the idea, that's the current knowledge we have.
Now that's fantastic when we consider these are the most abundant stars, plus they are orbited by a system of at least 3 planets. How many planets do we have in the galaxy then? This is going to be mind-boggling stuff.
On average, then we would have, let's say, if there's 100 billion stars in the galaxy, that would mean we have roughly 3 billion planets.
Incredible stuff.
It is.
So then, Proxima Centauri. You said 4 signals that you detected around the star, or from the stellar data.
Yes.
Now, how did you detect those 4 signals?
That's a statistical trick, and it's slightly on the complicated side, but we were trying to model the stellar variability as carefully as possible, just using what we call red noise models, knocking out correlations in the data.
Now, the stellar variability, just to introduce this concept, this comes from what we deem the magnetic properties of the stars, how variable these stars are. So we can look at the Sun, for instance, and we can see these regions, these spots, number 1, these so-called solar spots. And this is regions where strong magnetic fields are bursting through the surface, and we see a relatively cool region compared to the rest of the solar surface, or the photosphere as we call it. There's also hot regions surrounding those spots, these plages, and these features give rise to noise in our data set, and so you were working to try and remove or model those noise sources.
Yes, but we also tried to go further than that. For instance, we detected a tentative periodicity at roughly 2,000 days in a star, and we thought at the time that would be a signal caused by the star's magnetic activity cycle, just like the solar cycle of 11 years.
Indeed, yeah. And how did you manage to model that out?
At the time, it was only modelled as a simple periodicity.
So it could have been another real signal from a planet? Or
it could have been.
Indeed. Okay. And we may come back to that in a future video or so. But Proxima b, the 11-day planet, how did you pull that out of the data?
Well, that was a trick, because it wasn't the most obvious signal at the time, and it only became more obvious after we got high cadence observing runs, revealing really its existence and its nature. But at the time, it was a low amplitude signal of roughly amplitude of 1 meter a second, and that corresponds to walking speed, so we could see the wobbles of the star of going back and forth 1 meter a second.
Just imagine that. We are using equipment on Earth to observe stars light years from us, giant balls of gas, variable objects, and we can measure their velocity towards us and away from us at a velocity of walking speed, 1 meter per second. I mean, this is mind-boggling engineering feats we're talking about here.
Indeed.
Fantastic. And so you used those data sets that we obtained here in Chile,
yes,
to discover Proxima b using your modelling technique.
Yes, right.
And so we want to say, how much data did it require, or at that time when you were analysing it, how much data did we have in our hands?
I reckon there was about 200 observations from the ESO's VLT's UVAS instrument, and roughly about 100 other observations from HARPS.
From HARPS. And these are 2 instruments in the north of Chile,
yes,
the European Southern Observatory sites, and you were able to use those data sets to search for these 4 signals that you detected. That's what you were using, yeah. And so Proxima b, what did you think at the time when you found this signal? How reliable was your detection?
To be honest, I didn't think much.
Okay.
The reason was that the signal was very weak, and it was only... It was a borderline case, let's be fair, bordering on significant detection, but still slightly crossing it. Therefore, we could claim that we have detected something. Of course, we had no idea what its nature would be. We could not show that it was indeed caused by a planet.
Yeah, so it wasn't a unique signal at the time, but it was bordering on being real, something that you would put full trust in.
And also, more than that, it was supported by two different instruments, so we knew it could not be caused by instrumental biases or wobbles in the instrument.
And that's another key point of the survey you were conducting at the time, was the fact that this wasn't just one instrument you were using. We just said it was UVs and HARPS.
Yes.
And so you were looking for signals that were appearing in both datasets that were supported by both datasets at the time.
Yes, because any signal found in data from only one instrument could be due to whatever wobbles of the instrumentation or even small biases. And that's always a danger. We have to make sure we don't fall into that kind of snake pit,
which is very, very easy to do. So at the time, then, and I remember back to this time, let's talk about what we did with that data set. So at the time, you wrote a paper to announce those results.
Yes, in very uncertain terms though. The paper was claiming that we have found signals in Proxima Centauri data, and should they be caused by planets, our interpretation would have been that Proxima b was roughly one Earth mass object orbiting the star, but of course Proxima Centauri is the nearest planet to the nearest star to the Sun, so discovering a planet orbiting that one would be quite extraordinary. And at the time we didn't have enough evidence to claim that. And because extraordinary discoveries require extraordinary evidence,
that's for sure,
the paper was unfortunately rejected.
So then, at that time, we set out to try and test if this signal was real. That's what we aimed to do then. And so the way we did that was a colleague of ours, who was part of the original paper that Mikko wrote, was thinking about how he could set up a project to do that confirmation, and that became the Pale Red Dot project.
Yes.
Which became very successful and, let's say, somewhat famous in its own right for the excellent outreach that was done as part of that project. So at that time, the idea of the Pale Red Dot project was not only to gain more data of radio velocities that Mikko was observing to confirm the planet, but also to try and negate the stellar activity in a way of quasi-simultaneously observing the star with photometry. So that was another key part of the Pale Red Dot project, was not only to gain radio velocity data, this velocity, this movement of stars, of Proxima Centauri, but also to observe its photometry, to observe its brightness at the same time, or almost the same time, to see if we could constrain its activity and the rotation period of the star, which really affects those radio velocities. And also the flaring, because this is an important point also of Proxima Centauri. Proxima Centauri is a flare star, that we call, and that means there's these violent outbursts, more than 60 per day, and many, many strong violent outbursts across a year's period. And in that time, those flares can affect the measurements that we observe. That's correct.
Yeah, of course.
So we need to somewhat negate that as well, and using photometry can help us to track those variations. Okay, so what did we find early in the Pale Red Dot project?
Well, the Pale Red Dot observing project, it had only lasted for roughly 10 days, when we already knew we had verified the existence of the signal of Proxima b. Now, it was exactly where I predicted it would be. It had the exact same period I predicted, and there was no photometric variability, there was no spectroscopic variability caused by activity of the star that could mimic planetary signals in the radio velocity. So we were pretty sure at that time. That was in 2015.
Yes, and so this is, you mentioned 10 days. I want to make it clear that when we ran this project, we were taking data just every night of the star. And so it only took 10 more data points with the correct sampling or the correct observing frequency, which was every night, to say, bang, we have the detection of the nearest planet, exoplanet, to the solar system.
we were also very, very fortunate because over those 10 days the star wasn't showing very active features. It wasn't flaring much and it was quite nicely behaving. So that played in our advantage.
So there's also elements of, let's say, luck, because these, and I can't stress this enough, these observation campaigns, I mean, this is more than a decade of observations.
Yes.
It's more than a decade of observations by multiple teams, analysed by multiple people, analysing the data in different ways, and yet, with a little bit of luck in the end, we could quickly confirm the existence of Proxima b.
We could do that, but the most surprising bit for me is that nobody had done it before. I mean, again, Proxima Centauri is the nearest star to the Sun, so why did not anybody observe it over consecutive periods of, consecutive nights? And anybody could have made that observation.
But at least at the time you had analysed the data, we had a really strong reason to analyse it in nightly sampling. If you say that.
For us that was easy because we already knew what we were looking for.
Exactly.
And not only looking for, we were trying to confirm the existence of Proxima b, but also we were trying to, if it wasn't a real signal, we were expecting to be able to rule it out.
And it has to be said that we don't own these telescopes, nor these instruments. That's a pity. And so to gain this type of data set is no mean feat. 10 nights observing the same star, that's no mean feat.
Actually, we observed the star for a month, so more than 30 days, and our colleague Guillaume Anglada-Escudero was really smart in that respect. He proposed to observe the star at the beginning of every night, so it could be done in an automated way, so that no observer would have to go up in a mountain.
Indeed, and that was one of the key reasons I think this project was launched in the first place. So, coming back to Proxima b again, let's discuss one other aspect of Proxima b that I think really helped capture the public's imagination. And you know what I'm going to talk about?
Of course, I mean, it's not just the fact that it's the nearest planet to the solar system, it's also the fact that its mass is roughly one Earth mass.
Indeed.
Maybe slightly heavier. And in addition to that, it orbits the star in what we call the liquid water habitable zone, which means water on the planet's surface could remain in its liquid form. Yeah,
so an Earth-like, however we deem an Earth-like planet, but if we could take Earth, for instance, if we had the hand or the so-called hand of God and could move Earth around another star, we would position the habitable zone such that the planet, or Earth in this case, could maintain liquid water on its surface. Not too hot by being too close to the star, and not too cold by being too far from the star.
Except, of course, in this case, I mean, you're absolutely correct, but in this case, the planet orbits the star in only 11.2 days, which puts it very close to the stellar surface. And in case of Proxima Centauri, that we know is an active flaring star, there's a really nasty radiation environment going on the Proxima b surface. Ultraviolet radiation, even gamma rays that will just sterilizing the planet's surface.
So yes, this is another reason the habitable zone is actually quite a maybe tetchy subject to talk about, but certainly it's quite difficult to define for many reasons.
Absolutely, there are lots of things that could affect whether a planet can be habitable or not.
For sure. But if we just take this as the liquid water habitable zone, Proxima b falls where? Slap bang in the middle?
It's slap bang in the middle.
And that was one of the key points for launching not only the Pale Red Dot project, but it's what captured, in my opinion, or one of the things that captured the public's imagination. The nearest star to the Sun, Proxima Centauri, has a planet that has a mass potentially similar to the Earth, but also an orbit that can be looked on for various reasons to be similar to the Earth. It's in the centre of the so-called liquid water habitable zone.
Of course, the situation would be very strange from our own perspective because the star is a small reddish dwarf star, and And the year on Proxima B lasts only for 11.2 days here on Earth.
Yeah. So what age would you be if you were on Proxima B?
Oh, damn.
So, yes, that's one of the interesting points, that these small stars, M-dwarfs, their habitable zones are much closer, or liquid water habitable zones are much closer to the stellar surface than stars like the Sun. And that potentially makes it more volatile, a much more dangerous area than, say, where we are.
Possibly dangerous, but definitely different.
Definitely
very different. Something we have absolutely not seen anywhere in our own solar system.
And that's certainly the way to look at that. So finally, we have this fantastic planet, Proxima b, orbiting the nearest star to the Sun. And we mentioned already the reason nearby stars are important is that the follow-up potential.
Yes.
In your eyes, what's left to be done with Proxima Centauri or Proxima b?
The first natural step is to look for other planets orbiting the star. We have tentative evidence that there are others, except that we don't quite know yet their periods, their orbital periods, and their type. But we have good reasons to believe that observing Proxima Centauri in the future is going to be fruitful. And
there are teams, including ourselves, that are working intensively on that at the moment.
Yes.
To search for new planets, for new signals emerging in the data. What other way? So for me, another set of observations that we really should be thinking about, this is the nearest star to the Sun, and we have new generations of instruments coming, particularly those in Chile, like the Extremely Large Telescope, like the Giant Magellan Telescope, that are coming in the mid-2020s, so only a few years from now. And so this is a system, this is a planetary system that we can hope to directly image small planets, that we can resolve the very small separation between the star and the planet in the future, and imagine the outcome.
Quite possibly that's going to be the reality in the near future. It's a shame though that Proxima b does not appear to transit in front of the star, so we cannot observe let's say, properties of its atmosphere yet.
And we will talk about that in part 2 of this series on Proxima b. And that is a real shame, because we did spend a lot of effort trying to search for that transit. We'll come back to that. And so, we talked, just to wrap things up, we talked at the beginning about being able to maybe traverse this 25 trillion mile distance. Do we really have a project that could potentially send vehicles, send craft to Proxima b?
There's the Starshot project,
Yes.
And well, I'm a bit skeptical whether I'm going to be alive to see the outcome, but at least it's been planned, the planning is on the way, and it's quite possible that within 40 to 50 years' time we might see small fleet, or even one, robotic probe, very tiny in size, flying past Proxima b and even taking an image or two.
And just imagine that, imagine we had real in situ images of the nearest rocky planet in the habitable zone, the liquid water habitable zone of Proxima Centauri. I think that's probably the best way to end this video. Fantastic stuff. And I want to say to Mikko, thank you very much for your time, for coming on the show today.
You're welcome.
Excellent, it's been a pleasure to discuss this topic with you. And I'll see you all in the next show. And remember, it only takes you to ask the right question to change the course of history. Good night.
Violation.